So let's sync up a little bit of why this matters for methane, for dispersion, right? For the models that we build. So to go back over, air, just like water, just like this table, has mass.
Yeah.
Right? That mass is a fluid. It's moving about, at least when we're talking about air, freely in the atmosphere in many cases, but not always. We'll talk about obstructions and things like that, obviously, in the future. These balloons that you have represent whether it's air molecules or pockets of air and how they interact with one another.
Yep.
And so we're thinking about that. And then we're talking about the conservation of mass, meaning you're not destroying this. So even if you burn methane, I think a lot of people think that you may be not conserving the mass. All you're doing is chemically just altering the bonds, right? So the mass, you've actually destroyed nothing. You've just rearranged things. We can get into a future discussion of actually what happens with fusion. That's a whole different can of worms. So when we're talking about this, how does this have any implications on methane and how, if it's being released at a well site or at a landfill or at a dairy farm, why is it important to be thinking about this interaction?
Very simply, let's go back to the methane here. Okay, so let's say this chunk of methane that I'm interested in, it's in a pipe initially, or at least prior to being in the atmosphere, it's in a pipe or in some equipment, and it's contained. And we could go to that piece of equipment, and because it has fixed dimensions, because it's contained in such a vessel, we could measure its density, and through a fairly simple calculation, determine exactly what the total mass of that is. Now, what happens if we don't do that, and then there's a leak, and some of that mass then gets released into the atmosphere? Then that mass is now subject to everything that's happening in that local atmosphere. All of the wind, all of the complicated wind, all of the simple wind. Sometimes there's no wind. I mean, you've shown cases in the simulator tool where you have no wind. Well, what happens when you have no wind? Well, the stuff still disperses into a still atmosphere. You can have a still atmosphere. You can have a moving atmosphere. You can have an atmosphere that's aggressively moving in various different ways that we pretty much understand fairly well in terms of the atmospheric dynamics. Now, that mass of methane is now subject to all of those motions and begins to take up those cavities and spaces and move along those complicated wind fields. So what happens is if you have a sensor or a detector of some type that's out there measuring concentrations of methane at some location close to where you suspect that a leak might be, what you're picking up on is a methane that's already been displaced and moved around in this complicated atmosphere. You're catching a little glimpse of all of that dispersed. So imagine a way to imagine this is, imagine you have a cup of water in front of you and you just tip it over and watch the water flow in front of you and disperse itself around. It's the same amount of water, right? By conservation of mass, it's the same amount of water, but it becomes a lot more difficult to know how much of it is when it's all strewn around on the table. Back when it was on the glass, you could measure the glass and figure out exactly how much water you had. But now afterwards, once it has been subject to its fall and dispersion, now it becomes much more difficult. Now imagine that you can only sample a drop of that at some place on the table. And based on that, try to figure out how much water actually fell out of that cup. That's the kind of problem that we're talking about. And it's not easy, but it is possible. And what allows it to be possible is precisely conservation of mass. Because we have that constraint, and because we rely on that constraint, because we know that must be true on this planet, we can actually make the computations and create models that allow us to reverse engineer that process and almost look back in time and get back to a situation where we can say, okay, this is the amount of mass that had to have fallen out of the glass in order to flow around onto the table and become that particular footprint of dispersed fluid.
And just to frame up, I guess, how infinitely complicated it could get is if we knocked over that glass of water and spilled it on the table and we didn't pick it up and we sat here for a day, all of that water would eventually evaporate into the air. So the person who would come here after you wouldn't even be able to see the water on the table. But because of the conservation of mass, it's actually in the air around us. So put differently, you would still be able to calculate, assuming everything else was steady, the change in absolute humidity within the room itself, and therefore know that there must have been water spilt on the table, and you could exactly back out how much water was spilled on the table just by looking at that.
As long as you know that there was a change in these conditions and somehow be able to measure them.